A very good day to everyone. I'm Dr. Amita Kappor, author of best-selling books on deep learning and TensorFlow, a deep learning framework. I will be taking you to the most exciting field in deep learning, reinforcement learning. It is my favorite area, and I hope by the time you finish the reinforcement learning day at NMA, you also find it fascinating. In machine learning, we classify learning in three types: supervised, unsupervised, and reinforcement learning. Supervised learning is learning with teacher. Here, the training data contains for each input the corresponding label. Unsupervised learning is learning without the teacher. The agent builds the inner representation of the training data itself. Reinforcement learning is in between supervised and unsupervised. There is no teacher to tell if the present outcome is right or wrong, but it has a feedback from the environment in terms of reward. It is inspired from how the animals learn from experience. For example, to train a dog to do tricks, the trainer reinforces the good behavior by rewarding dog with treats. Now, to understand reinforcement learning and to be able to implement it in a computer program, it's important that we formalize the deep reinforcement learning framework. So it starts with an agent. So we have a reinforcement learning agent and it exists in an environment. The agent knows about the environment through the representation of the state of the environment as a vector S. Now, this information can be a complete information of the environment or it may be a partial information of the environment. The agent can perform some actions on the environment, that is, it can give commands to the environment. An environment in return can give feedback to the agent in form of rewards. So you can think it of as learning with a critic, where environment is the critic evaluating each action of the agent. The basic idea is that the agent learns a policy pi that maximizes the future rewards. An important thing to note is that reward is not instantaneous. It is not so that for every action, agent gets a reward. If that was so, it would just be a supervised learning problem. The reward comes later. It can be few steps later or just at the end, like for the mouse in the maze. Mouse gets the cheese only after coming out of the maze, once after many steps. At each time step, the mouse assesses its immediate environment. Based on that, it makes some actions. It can move left, right, up, down, maybe just think for some time. And only when it reaches the goal, that is end of the maze, it gets the reward, the cheese. Despite delayed reward, the goal of the mouse agent is to learn what actions caused it to receive rewards. In that sense, we can call reinforcement learning as also semi-supervised learning with rewards as time-delayed labels. Another important thing to note is that unlike other learning frameworks, here the consequent states are not independent of each other. At each state, agent takes an action to reach the next state, and thus we can say that reinforcement learning is a sequential decision process. There are certain definitions that we need to understand as we go through the reinforcement learning framework. So the first thing is the state space. So state space is set of all possible states the environment can be in. The state space can be continuous or it can be discrete. So for example, if I take the two cases here which have been taken from the book, in the first case is that there is a robot and it has to find its path through a maze. So the state can be represented by a 4x4 array with elements telling whether that block is empty or occupied or blocked. A block with a value 1 means it is occupied by the robot, a value 0 means it is empty, and X represents that the block is impassable. Each element in this particular array can have one of three discrete values. So we will say that here the state space is discrete in nature. On the right side, what you can see is a self-driving car agent. The agent is taking as input the front view image, and the image contains continuous valued pixels. So here the state is continuous. Also observe that while in the case of maze, our state space contained information of the entire environment. For the agent driving the car, only the immediate neighborhood is observable. Thus, it has partial knowledge of the environment. Next, we talk about the action space. Action space is the set of all possible actions A, and they depend upon the present state S. Actions may or may not result in the change of state. Like states, they can be discrete or continuous. Again, coming back to the same example, for the robot finding a path in the maze, there can be 5 possible discrete actions: up, down, left, right, or no change. While the self-driving car agent can rotate the steering wheel in a continuous range of angles. Next comes the reward. The reward is a scalar value returned by the environment based on the agent actions. Now you can see that the reward is a function of the present state S. It is also a function of the state S dash, that is the state of the environment after the action A has been taken. The reward is determined by the goal. The agent gets a higher reward if the action brings it near the goal, and it should get a low reward or a negative reward otherwise. How we define a reward is up to us. In the case of the maze, we can define the reward as the Euclidean distance between agent's current position and goal, while in the case of self-driving car agent, the reward can be that the agent is able to retain the car on the road. That is a positive reward, and in the case the car moves beyond the 2 rate boundaries, then it is a negative reward. The goal of the agent is to learn a policy. This policy is mapping between the state and the actions to take in that particular state. The policy can be deterministic, that is, for each state there is a well-defined policy. Again, in the example, for the maze robot, a policy can be that if the top block is empty, move up. The policy can also be stochastic, that is, where an action is taken by some probability. It can be implemented as a simple lookup table, or it can be a function dependent on the present state. The goal of an RL agent is to find an optimal policy, the policy that maximizes the future rewards. That is the optimal policy. Now, another important parameter for finding optimal policy is the return. So when we talk about the return in reinforcement learning, what we mean is basically the discounted sum of all future rewards starting from the current time. It is basically the sum of the rewards multiplied by a factor, that is the gamma factor. So R is the reward at time t and gamma is the discount factor. The value of gamma lies between 0 and 1. The gamma factor determines how important future rewards are in deciding the policy. If it is near 0, the agent gives importance only to the immediate rewards. But a high value of discount factor means that the agent is looking far into the future. It may lose immediate reward in favor of the high future rewards. For example, in the game of chess, you may sacrifice a pawn for checkmate of the opponent. And it is because it is being multiplied by the gamma factor, it is also called as the discounted total return. Now, important function based on the return is Q function. It is the expected total future reward an agent in state S can receive by performing action A. And the importance of Q lies in the fact that if the agent knows this Q function for any state action pair, then the agent can use it to determine what is the best action in that particular state, or in other words, it can use it to determine its policy, the optimal policy, the one that maximizes the rewards. So what we do out here is that we choose argmax of Q function as our policy. That is, we choose the action which gives the highest Q value. A related function with Q value is value function. It is a very related term and it is normally used in the value-based learning, and it is the expected total reward from the state S after following the policy pi. So I've kind of introduced you to some basic elements of reinforcement learning lingo, but there are a lot more, and as you will go through the NMA tutorial on reinforcement learning, you will learn about many other new concepts. For example, the Markov decision processes, the Bellman equations, and so on. The focus of this talk is the applications of reinforcement learning and future research options. And the idea is to keep you motivated. Okay, so we come to the applications. The first application is in the field of games. Games are the most natural application for reinforcement learning. A game has states, rewards, and actions, and the gamer performs action to reach a particular state of the game. And along the way, they accumulate some rewards. Since actions build the next state, we can see that games require a sequential decision processes. The games like chess, Go, they offer challenge in terms of the large state space and action space, making traditional search algorithms insufficient. Yet the breakthrough in games came in 2013, when DeepMind demonstrated the amazing power of reinforcement learning. They showed that deep Q network can be used to achieve human-level control in the game of Atari. Last few years have been golden period for reinforcement learning, with AlphaGo defeating Lee Sedol, the Go master, in 2017, and then AlphaZero defeating AlphaGo, starting from tabula rasa. The most amazing part was that AlphaZero learned via self-play. That is, it taught itself how to play by playing against itself many times. If you see the games played by the reinforcement learning agents, what is most amazing is that they choose strategies which humans normally would not. For example, in the breakout game demonstrated in the middle, agent learned a particular trick to strike the ball via edges. So, as a result, forcing it to strike the wall first and then the bricks. And doing this, it could find a way of breaking all bricks by first breaking the bricks at the center, and then once the ball crossed the center, it stayed there on the top and it didn't have to do much, right? Another area, the traditional application area for reinforcement learning is robotics, and the techniques that are learned here, they can be applied to wide range of areas. For example, automation of manufacturing units, supply chain, etc. What you are seeing here is a dexterous robotic arm, trained using truncated natural policy gradient algorithm. The goal of the hand is to rotate a valve. The negative distance between the current and the desired valve orientation is used as the reward function. The agent is trained on the real hardware. The agent, in this case, the hand, must figure out on its own how to move to rotate it. As you can see, after 90 iterations, it is able to rotate, but fumbles. But after 9 hours of training, it does it like a pro. Using exactly the same algorithm, the robot can learn rotating valves made of different materials like foam, shown on the extreme right. It has been observed that if we first train the robot using human demonstration sample, followed by reinforcement learning, the training is faster. Since reinforcement learning involves a lot of hit and trial, it is much easier and often cheaper to train the robot in a simulated environment, for example using Gazebo or Unity. Both have a large number of physics-based models for a variety of industrial robots as well as environments. The simulation provides us with large number of data which can be used to train the agent and accelerate training. Most problems in finance and economics are decision problems with sequential nature. Reinforcement learning is a natural solution method. It has been used for portfolio optimization, making an optimal policy for trade execution, and even offering best price to customers in the insurance agency. In each case, the reward functions are defined so as to optimize the profit or revenue. For example, in case of pricing strategy for insurance, the agent has to propose the price such that the net revenue increases and the old customers are retained. If we consider the two goals, they are in opposite directions. It is easier to increase the price and increase the revenue, but in the correspond as a consequence, we might not be able to retain the old customers. On the other hand, to retain the old customers, offering a low price may be a better solution, but that can result in decrease of revenue. So the goal of the agent is to satisfy both, that is, increase the revenue at the same time increasing the customer retention. Reinforcement learning has been applied in the field of transportation. So for example, it has been used to find an optimal policy for ride sharing. Reinforcement learning agents have been trained to generate report from medical images like X-rays. And here the human prior knowledge is integrated with the deep neural networks to generate the medical report. Even in the field of energy saving, Google showed that they can reduce the energy consumption of data center cooling system using reinforcement learning. Next, we take up some future research directions in the reinforcement learning field. One of the areas that has captured everyone's attention is the area of automated machine learning, AutoML. The idea is to build a system which can, for a given data, find the best model and the best hyperparameters. This should reduce the huge cost of handcrafting machine learning solutions by making the whole end-to-end machine learning pipeline more automated. AutoML pipeline consists of three major macro steps: data preparation, feature selection, and automatic model generation. The AutoML searches for the best model architecture as well as the hyperparameters for the selected features. Under the hood, AutoML uses either reinforcement learning or evolutionary algorithms with the goal of maximizing performance. It has been observed that AutoML obtains best models even when compared with handcrafted ones and takes less time, as is shown in this graphics. So this is the transformer. The blue ones are the handcrafted ones and the red one is the AutoML evolved transformer. Deep reinforcement learning algorithms are often sensitive to the choice of internal hyperparameters of the neural network architecture. And thus, we cannot apply them out of the box to new environments. Tuning hyperparameters of reinforcement learning algorithms can quickly become very expensive, both in terms of high computational cost and a large number of required environment interactions. When we talked about the AutoML, we had supervised learning algorithms, so the data set was fixed. But in reinforcement learning, due to environment interaction, data is moving, data is changing. Additionally, what might be a good strategy in the beginning may not work as the agent becomes more learned. So it would be great if we had a system which can perform hyperparameter optimization of reinforcement learning algorithms automatically, something like AutoRL. One approach towards AutoRL for hyperparameter optimization is shown in the figure. It is SERL, that is Simple, Efficient, Automated Reinforcement Learning. Now, you can see that it is a population-based hyperparameter optimization approach, and here each individual in the population represents a deep reinforcement learning agent. The agent consists of a policy and a value network and the reinforcement learning training algorithm hyperparameters, including the neural network architecture. The training and the meta optimization of these individuals takes place in an evolutionary loop that consists of 5 basic phases: initialization, evaluation, selection, mutation, and training. During one epoch of this evolutionary loop, all individual properties could change through different mutations as well as training operators. This happens independently for each individual and can be processed in parallel. This particular work is part of ICLR 21. Another thing that is important for reinforcement learning is deciding the right reward function. That is very critical for training a reinforcement learning agent. There are works by Google to build an AutoRL system where both the reward function and the network architecture is automatically determined using AutoRL approach. They combine both evolutionary algorithms along with the heterocritic network architecture to do the same. Despite all the breakthroughs in artificial intelligence, we are still doing narrow AI. The area where AI is employed for a specific field like playing Atari, driving car, and so on. We are still very far from the holy grail of AI, the artificial general intelligence. AGI focuses on the study of systems that can perform tasks successfully across different problem domains, while AI typically pertains to domain-specific expert systems. General problem-solving ability is one that humans naturally exhibit. At a high level, we can think of the intelligence demonstrated by biological systems as consisting of 2 abilities: the ability to generalize the perceived data and the ability to make right decisions, perform right actions in the perceived environment. Thus, combining deep learning architectures with the reinforcement learning can pave way to AGI. One can argue that intelligence involves 2 complementing subsystems: perception and actuation. Perception can be thought of as mapping sequence of observations possibly received from multiple modalities to an inferred state of world with which the intelligent agent interacts. And actuation can be thought of as the goal of selecting actions to be taken at any given time so as to maximize some utility function. Another interesting approach towards AGI is using cognitive architectures. Cognitive architectures are essentially a theoretical model that attempts to represent the underlying infrastructure for an intelligent system as accurately as possible. One of the popular cognitive architecture is Clarion, proposed by Sun. It consists of 4 subsystems and follows a hybrid approach. One of the main components of the architecture is goal setting and reinforcement. Reinforcement learning world is vast, and this graphic shows a detailed taxonomy of the reinforcement learning algorithms. In the 30 minutes time, I could just give you a bird's eye view of this vast RL zoo. I've shared the research papers covering each of the applications and future research directions in the talk, with the thought that you may want to know more about them after learning the reinforcement learning basics. I hope you enjoyed the talk and it served the purpose in motivating you to the amazing area of reinforcement learning. Thanks for the time.